All right, so good morning, everybody. I am thrilled to be here. And as you'll quickly learn, I love to talk about DARPA. So you may have to raise your hands in defeat if you're getting a little too much from me. I did plan to make sure that I've got time for questions from you, though. So my goal today is to give you kind of a glimpse of what DARPA is up to in areas that we think you might be interested in. I'm also happy to segue into anything else we're discussing, but I'm going to start off by giving you a little bit of a kind of a DARPA 101 to help put everything that we're doing into context. And then I'll dive into, kind of a panoply of different communications-related programs that we've got underway. So to start off, DARPA was started in 1958 in response to what was, at the time, a really big strategic surprise for our government, and that was the launch of the Sputnik satellite. From what I understand, as often happens within scientific communities, it wasn't maybe quite as much of a surprise, but the politicians were upset, and they vowed that this type of surprise should not happen again. And they did a number of things. Among them, they created NASA. And then they created this little agency called the Advanced Research Projects Agency, which was designed to create technological surprise. So it's kind of hard to avoid surprise in the sense that we don't have the magic crystal ball yet. But the idea was that if we could be technologically leapfrogging ourselves, then we would have the chance of being the creator rather than the recipient of technological surprise. So we've been doing that ever since. I think we were lucky to have started in a time when the government was a much smaller organization and a little less bureaucratic. The original agency had a lot of freedom and flexibility, and as they moved through time, they kind of had enough success to earn the freedom and flexibility that we have been able to maintain ever since. So our mission is to make pivotal early investments that change the trajectory of technology, and we do it across pretty much every imaginable technological field, and maybe even not so technological, because we're starting to move into social science, which is really hurts my head. But if you look at this timeline, there's sort of two categories of things to think about in terms of DARPA's greatest hits. On the top, you'll see systems. So these are big military systems, including a lot of the early work in communications and networking. Of course, stealth aircraft, uncooled infrared night vision, miniaturized GPS receivers, and other forms of precision guidance and navigation, unmanned aerial vehicles, things like that. On the bottom, think of the enabling technologies. This is like university work, a lot of small companies. A lot of the kind of work that I would imagine folks in this audience like to think about. So we invented material science as a discipline. That's a little bit of an exaggeration, but basically before DARPA, you had metallurgists and chemists and maybe mining engineers all running around and not talking to each other a lot. And we sort of forced them all together. And that led to a lot of really breakthrough work in different kinds of metal alloys, composites, and of course, semiconductor materials. Information technology, you might have heard of this little experiment that DARPA conducted called the ARPANET. That grew up and graduated to become NSF's research network, which then, with the help of politicians, and I have to tell you this, that includes Al Gore, the legislation went into place to turn it into the internet, which we know and love and maybe sometimes don't love so much, but it's kind of a good example of how DARPA works, because we made those early investments to change what was possible, but it was really a much bigger community and ecosystem that turned it into what it was. We have been working on AI since the beginning, and as you can see on those timeline bars, there are a number of AI winters where we stopped, waited for the technology to kind of become interesting again, and moved back in. Of course, we wanted to make sure we highlighted a lot of our early work in the underlying technology related to software-defined radios, work in microelectronics. We did a few really interesting competitions. By the way, the hissing is driving me crazy. I hope it's not driving you crazy. If you're okay, then I'm good. To challenge self-driving cars in a race. The very first one resulted in some fantastic crashes and flaming wrecks. Not a single vehicle crossed the finish line. But my predecessor demonstrated the kind of courage that I hope that I will always be able to have, which is going in front of the news reporters, to report that we had utterly failed and we were going to do it again the next year. And the next year, multiple vehicles crossed the finish line. A few years after that, we made these self-driving cars operate in urban settings, and the winners of those vehicles pretty much all got hired by Google, and thus the self-driving car industry was born. Whether this is a good thing or not, I'm not sure. We are responsible. We're directly responsible for Siri through a program that was originally called Personal Assistant That Learns. And most recently, and I think it's a good thing because it's a little bit of the reason that we're all physically able to be in this room, those of you who are here, is an investment about 10 years ago in vaccine technology. We had an Air Force officer, a medical doctor, who was really worried about the fact that we send our service members all over the world, and they're vulnerable to all kinds of diseases for which they have no immunity. And the methods we had for making vaccines were just ridiculously slow for what the military needed. So he started a program that invested in nucleic acid-based vaccines, including messenger RNA. And there was this little company called Moderna, which you might have heard of, that was one of his earliest performers. So I went through that to try to give you a sense of kind of the breadth and the depth of how DARPA works. We are very, very risk tolerant, and I think it's worth mentioning our business model. Tom talked a little bit about being a program manager. The heart and soul of DARPA really is our collection of program managers, and at any moment in time, we have about 90 or 100 of them, and they come to us from all walks of life, strong technical experts, but they can be academics, they can come from industry, they can come from other government labs. We're even starting to explore the idea of potentially having one or two coming from our allied partners in countries like Australia or the UK. They come for a temporary tour of duty. While they're with us, they have access to a $4 billion budget, and they're told to change the world, but they only have about 4 years. And so if you've worked with DARPA program managers, if you've worked with Tom, you know there's a little clock ticking in the back of their head. There's this sense that I get to change the world, but time is running out. And so they will go out there and they will fund lots of things fairly quickly in order to assess the landscape. They will start big programs with the understanding that they might fail, because it's a lot faster to try something and fail than it is to spend months and maybe years thinking about it and trying to overanalyze, all the things that could possibly go wrong. So that's the context of DARPA. What I'm going to talk about now really is the far right. We don't spend too much time on the past because really we're thinking about the future. That's all my program managers care about, and that's what we're investing in that maybe a successor of mine a decade from now might have the opportunity to brag about. So these bubbles show DARPA offices. I'm always a little uncomfortable about DARPA offices. We have 6 of them. And I tend to think of them as homerooms for our program managers, because really the fundamental unit of action in DARPA is the program manager. Within the offices, they receive administrative support, technical support if they need it, mentoring, obstacle removal. But we don't organize our offices in such a way that they are not designed to tell the program managers what to do. But nonetheless, I have 6 offices, and 3 of them are highly relevant to today's conversation. One is the Microsystems and Technology Office, which is focusing very heavily, as you can imagine, on microsystems. So think of them as the hardware space, and we've got some themes that they've been focusing on, including directional and millimeter wave technologies, a lot of new work in smart devices and components, and I'll highlight some of those in a minute. Our Information Innovation Office lives and breathes software, and for today's conversation, it'll mostly be about software security, but as you can imagine, they are deeply involved in AI and machine learning techniques and trying to figure out what the next wave of artificial intelligence really is, because they are convinced that machine learning is nowhere near what we actually would need to solve problems where we could put any real trust into devices. As you can imagine, in the military, we have to trust our software with our lives. And right now, it would be foolish to do so with purely statistically based machine learning techniques. And then at the bottom, we have our Strategic Technology Office, which is a systems office. So they will often be putting together things that come out of offices like MTO and I2O into these bigger systems or even systems of systems. So what I'm going to do now is I'm going to kind of take you on a tour. Think about starting in the upper left corner. We're going to focus on hardware and how that might apply across the military national security domain, so the battlefield. in this particular case. Then talk a little bit about security, both software and hardware, and then we'll move into talking about systems. And then I'm just sort of plucking random programs out based on feedback from Tom and some of his colleagues into what we thought might be of great interest to you. But of course, I'll be happy to answer questions on things that I might have missed. So, it's really hard to give a Department of Defense talk if you don't have one of these, what we call OV1s, overview charts, with lots and lots of lightning bolts. And at least, since this is related to communications, those lightning bolts are actually kind of relevant. They look a little weird sometimes when people are showing like underwater pictures and things like that. So what I want to say is that each one of the things you're seeing is a DARPA program. The fact that each one is like right next to a platform is utterly irrelevant. Okay, so any one of these things, for the most part, could be on a satellite, an aircraft, a ground vehicle, or even a surface ship. We didn't have the artistic skill to figure out how to get the ocean in there at a reasonable scale. With one exception down at the bottom, the DEPRIVE program, which I'll talk about, one of Tom's babies, is not likely to be operating in real time on any of these field systems. But just to highlight a couple of things, the MIDAS program, for example, the title, the little description sort of says it, millimeter wave multi-beam digital phase arrays. This is a program that seeks in the next few years to be able to demonstrate a 256 element array operating with multi-beam functionality across the full range of 18 to 50 gigahertz. Lots of hardware miracles have to happen before we can actually get to that. ELGAR at the top. Again, arrays, focusing this time particularly in G-band, 110 to 300 gigahertz. Again, lots of hardware challenges that have to be overcome. And there are several other of these I'm going to highlight with a little more detail, starting off with that tour of security-related topics I mentioned. So we're going to talk about SIF and GAPS next. So SIF, System Security Integrated through hardware and firmware, that acronym just does not sing to me. So we just go with SIF. But SIF kind of operates on the assumption that both software and firmware attacks are typically exploiting some vulnerability in the hardware. And so the whole point of this program is to go after these fundamental hardware vulnerabilities and close them off. So these might be things like buffer errors, information leakage, incorrect sort of permission spaces, system of sort of implementation errors and things like that. So the idea being that if you can close these off within the hardware and actually in the chip design, you're eliminating entire classes of things that you would have to worry about doing software security updates on. SIF was pretty confident in its capabilities. They actually ran DARPA's first ever bug bounty. It was, so you're going to love this, finding exploits to thwart tampering or FET. And I think there were a whole bunch of other sub-programs in there that have connectivity to kind of the SIF and FET theme there in terms of what they named things. But it was 3 months, over 580 security researchers were attacking these sample systems to try to find weaknesses, and none of them were ever successfully exploited, and only 10 vulnerabilities were actually found over a 3-month period of prolonged attack. So it does give you the sense that if you know what you're doing, you can actually design hardware in such a way that maybe the software people can not have to be quite so precise and careful about what they do, what you do, right? So potentially make your job a little bit easier. GAPS, Guaranteed Architectures for Physical Security, has kind of a similar set of goals, but this really focuses on physically creating within the chip itself kind of air gaps. Or in other words, you want to physically cordon off that parts that you want to keep secure so that you can have both unsecure and secure levels of processing happening on the same device. So it's just a different technique, but it was different enough and unusual enough that it kind of merited a separate program to do a deeper dive. Now, if we think a little bit on the software side, and this might be a little closer to your heart, we'll talk about our Open Programmable Secure 5G or OPS 5G program. So I think this one, the diagram is relatively self-explanatory, particularly for this audience. Right now, you've got an opaque integrated software hardware system, lots of proprietary information. DARPA is focused on working in partnership with the Linux Foundation, this secure and open source development environment. And the program itself consists of lots of companies and academics, basically what we call performers, exploring the space of what you can create in software that can get us to this bigger vision of a much more open and a fundamentally much more secure capability. We have a brand new program on the right called Gecko. The broad agency announcement is on the street. This follows the similar theme of Ops 5G in the sense that we in the DoD want to take advantage of existing commercial capabilities, but we need to provide the security that makes it usable for us. So Gecko is focusing on creating these communication channels on unsecured networks that would allow privacy protections for the users. And that, as you can imagine, there'd be very interesting and useful commercial capabilities as well if we're successful in making that work. But if anyone is interested, proposals are probably due in about 2 weeks. And even if you had known about it before it came out, you would have only had 45 days at the most, just so you know. Everything about what DARPA does tends to be accelerated. So if you're interested in any aspect of this, what I strongly recommend on any program I talk about is to go to our website, get the name of the program manager, and go talk to them. Because even if the program is already underway, you might learn about something that keeps them up at night that is relevant to what you do, and you might be able to kind of separately design a new concept or a new thing to sort of explore together. All right. Now, next OB1 chart, but it's also the last one. These, and no lightning bolts. This is going to think a little bit more about modalities. So not just about the devices that are being made. Oh, and actually one thing I forgot to mention, on that last one, when you saw all of the little satellites and aircraft and the systems there, that is very much tied together to something that we've got underway called the Electronics Resurgence Initiative. So about three and a half years ago, we recognized that, one, we had sort of managed to offshore almost all sort of semiconductor manufacturing capabilities, which is not a great supply chain situation. From a national security perspective, it's not great. And of course, from all the other issues related to chip supply chains that I think everybody has been dealing with, it's not a great situation. That is something that obviously the Chips and Science Act and other things that are happening are supposed to deal with. DARPA's role is not to solve that problem. Our role is to figure out how to go to the next generation and kind of out-innovate what's kind of happening everywhere else. And so fundamentally, we tied ourselves to Moore's Law. We were all fairly convinced that without a significant change, well, I mean, we knew that without a significant change that we were going to be plateauing and you were not likely to see any processing improvements in the coming years. So we made a series of big bets to look at what came next. As a result of that, we were focusing on security, we were focusing on new materials, we were focusing on being able to process at greater speeds at the edge, kind of at the battlefield edge. But as a result of that, I think we are sort of all in on 3D heterogeneous processing, heterogeneous chips. So completely different materials stacked together, moving vertically. So we can run out of room horizontally. We've already run out of horizontally, we're sort of stacking. But this tremendously hard problem of working across different materials that were never designed to operate effectively together. So most of the programs you saw on that past overview chart are tied to that original Electronics Resurgence Initiative. We are kicking off ERI 2.0, where we're going to focus on manufacturability and real-world environments. So in space, deep sea, high pressure, radiation, whatever situations might have. So that leads me into this topic because, in the Department of Defense, we do have to think a lot about not just free space. We think about underground, we think about operating underwater, and we tend to be thinking about things that have to cross a lot of different domains. So this is a little more focused on a couple of different themes. One, gateways that would enable different kinds of systems to work together. Just as before, with a couple of exceptions, where the little program names are relative to the drawing doesn't matter that much. The two where it does matter, I'll talk about in more detail in a minute. But the bottom line is we need to have everything, as flexible as possible. We need things in the smallest possible form factor with the greatest possible performance. And that, if you wanted to just design an imaginary DARPA program, you pick whatever it is, and your goal is to make it 100 times smaller, 100 times faster, and figure out what technical miracle you would need to achieve to get there. And if you could also have it use no power, that would be even more awesome. So, yeah. So that's the common theme. But here, to highlight, a lot of what we've done is looked at kind of physical and software-based gateways. So Dynamo, right there in the center, that's a program that allows, for example, our Marines and our Army, who you would think would have radios that talk to each other, actually talk to each other because their networks inherently don't talk to each other, right? So these are software solutions to be able to make those connections. The success of Dynamo led to the birth of a program called Mink right below it, which is really looking at this kind of network of networks optimization path where it is constantly tracking all of the networks available and figuring out optimal routing of any communications or any information that needs to move across them. And I think I've got a picture in a couple of slides that will give you a better idea of what that looks like. So let's do that, and let's talk about first a couple of these domains. Remember I mentioned there were a couple of things where it actually did matter where they were on the chart. Timely is both underwater and in free space, and Space Bacon is focused on outer space. So these are things that might be of interest from a sort of a software radio perspective as we move into these new domains. First of all, when I say Space Bacon, did anybody chuckle? Do we have? Okay, so it's not just an inside joke for the Air Force. This is an homage to an existing system called the Battlefield Airborne Communication Node, or BACN, which fundamentally acts as sort of this gateway between all different kinds of RF systems. That was also initiated by DARPA, by the way, back in the late 90s. And so Space Bacon actually stands for something slightly different, but it's the same basic idea, only for optical systems. And if you've ever spent time thinking about the fact that you've got all of these different commercial networks of proliferated low Earth orbit satellites going up, you might have wondered, were these companies talking to each other and designing their systems so they could interact? And if you've been around for more than a year or so in this world, you know the answer was no. And sure enough, the DoD was thinking about our own systems, which would have yet another different set of modalities. So Space Bacon is meant to create these optical gateways that will go up there and connect all of the different low Earth orbit communication systems. Space Bacon, by the way, also was a fun opportunity for us to try to innovate in being able to get more commercial companies that have never worked with the DoD involved in helping solve our problems. So for any of you that have sort of felt like there is this immense barrier to entry, we've got a lot of people in this domain that are working at ways to sort of knock some of those down. And I'd be happy to talk offline for anyone who might be interested on things that we're initiating in that space. That includes access to classified work, even if you've never had a clearance before. So hopefully that's exciting. It's definitely exciting to me because, as you can imagine, it limits our choices and our ability to solve hard problems if we can only go to the small handful of people who are already on the inside. So that's Space Bacon. Timely is really focused, the cool part of Timely are those little UUVs that you see down there. They sort of drift up and down, and they're broadcasting across acoustic channels, and then they're getting and receiving information from RF. So the idea is that if you have a whole network of these sort of bobbing up and down at different times, at any one moment in time, one of them is up where it can hear, and then it goes back down and it's transmitting across the acoustic space. So, but I don't think Tom mentioned this. By training, I'm a geologist, so RF way too fast for me. Acoustic is at least starting to get into that slow mode. Now, when you move into geological time, then I'm with you, right? So millions of years. But we're very excited about the fact that with Timely, you could actually broadcast across a large acoustic area on the order of a few hours, which doesn't seem super fast, but if you are used to living underwater, it's way better than the speed of light, right? So there's a lot of excitement about being able to do this. So, okay, then I promised I would come back and talk a little bit about Mink, but I don't think I have to say a whole lot about SDR 4.0. This was this was one of your inventions, right, Tom? Right, but really focusing on kind of the GNU radio scheduler and optimizing it to enable a whole bunch of new capabilities. So we're excited about what that does community-wide and specifically for a lot of our programs. And then here's that layout of the MINC program. So the idea is that you might have space, air, ground, sea, networks. This is then creating that network of networks where it's keeping track of everything out there and then optimizing whatever communications path you need to get information from one point to another. So it builds upon some of the successes from that Dynamo program. All right, and then you've been very patient. I just have two more I wanted to talk about. My talk is a little bit of an homage to Tom Rondeau because DPRIVE is also his program. You started it, right? Yeah. So this comes down to talking a little bit about security. How many people here are familiar or have ever tried to write algorithms dealing with fully homomorphic encryption? Okay, so fully homomorphic encryption, this is basically mathematics, and the idea is that, you know, in the typical world, if you want to protect your data, you can only protect it at rest, right? When it's sitting somewhere, if you want to actually operate on it and you want to do something with it, you have to unencrypt it first. And that's kind of not what we actually want. So with fully homomorphic encryption, you can actually operate on encrypted data. So you can imagine this could be really useful in the banking industry. It could be really useful when you have different partners working together who want a shared outcome, but they may not want to share the real core secrets of their own intellectual property. From a Defense Department perspective, this could be a kind of situation where we're working with a lot of allied nations. And again, we want to be able to present integrated defense capabilities, but we're not quite willing to share the secret sauce with our partners about how to do that. Can you do a calculation that would talk about whether or not your overall system has the capabilities that you need? So this sounds great, and we actually had a program a few years ago that went all in on developing new algorithms and kind of focusing on the underlying mathematics. The problem is that to solve any practical problem, you would need at least weeks, maybe a lot longer to get there. So DPRIVE was focusing on the hardware accelerator part of the problem to say, what could we do to actually make this practical? We're not trying to get to a point where this is going to be a chip in an aircraft flying somewhere. What we're trying to do is get it so that calculation time goes from weeks down to seconds, so that it actually becomes usable and practical for certain classes of problems. But for those classes of problems, this feels like a huge game changer. And very, very, very hard to do. I think the bets are still out as to whether or not we think it's really going to make it or not. But it's absolutely worth it. And early successes caused us to kind of double down on it to see where we're going to see if we can actually help get it across the finish line. And then on the very first, that kind of overview slide, you might have seen down in the corner domain-specific system on a chip. So this is another thing that might be of interest to you all in terms of sort of hardware innovations. This is focusing on kind of finding that sweet spot in between general purpose processing and specialty processing. And the idea is that you're going to create a whole bunch and combine different processors that might operate usefully across a domain. So they're customized and optimized for a certain class of problems. But then within that class of problems, you have all kinds of flexibility and programmability in order to work on individual applications. So I think within that, not just with the hardware, there is a whole tool stack that they're working on in order to make sure that users have and programmers sort of have the flexibility to do that kind of hardware-software co-design. I should mention, I think that's also an interesting aspect of DPRIVE as well, which is that it's not just about creating the hardware in a vacuum. It is about co-design from a hardware, software, and algorithm perspective, because you really need to have all of those optimized across each other. Okay, so I have just take advantage of the fact that I have you as a captive audience to come back to the bigger DARPA story, do a little bit of a shameless plug for a series of activities that are underway right now. So give me 2 minutes of your time before I take questions, and enjoy this.
Coming to DARPA is like grabbing the nose cone of a rocket and holding on for dear life.
DARPA's a place where if you don't invent the internet, you only get a B.
The DARPA program manager quite literally invents tomorrow.
We are thinking about innovation unconstrained. Where can we go?
Predict what is emerging as threats.
We're looking for the applications that seem impossible.
That passion will be saving lives 5, 10, 15 years from now.
Coming to work every day and being humbled by that.
The innovation and collaboration, it's a team effort.
We're not builders of the ultimate technology.
It's the engineers and scientists at the companies and universities that we fund that ultimately are going to bend metal and write code and deliver these capabilities to warfighter.
DARPA is not one person or one place. It's a collection of people that are excited about moving technology forward.
And DARPA Forward is the name of a conference series that we're in the middle of right now. So if any of this has appealed to you, first of all, if you've ever worked on a DARPA program, you are part of DARPA. If you're ever thinking about doing it, think about attending either virtually or in person the DARPA Forward conferences. We have 2 under our belt. Next week, I'm heading to Columbus, Ohio. And as you can see, it's a little bit of a brutal travel schedule for us. It's a lot more fun in person, but we have done everything we can to make the virtual experience good as well. And we've put a couple of our folks through, living this virtually, and they say it's actually not bad, which I think is, which is pretty good. But the bottom line is we're trying to give people a little bit of deep immersion into the DARPA experience for a day and a half. So if you've ever wanted to come hang out with DARPA PMs or tell them what they're doing wrong or what you think they should be doing better, I'm just throwing this out there as your opportunity. And with that, end of the shameless DARPA commercial, and I'm happy to take questions.
Very, very cool stuff. Do we have any questions in the audience for Dr. Tompkins? And we do over here.
Thank you so much for the awesome briefing, by the way. So my team has been thoroughly exfoliated by the DoD acquisition process over the past 3 years. How do we close the so-called valley of death with getting things bolted to things in the real world?
Yeah, the valley of death is the infinite question for which there are an infinite number of answers, some of which are useful at any moment in time and the rest are not, right? So I'm gonna lean in on where we're doing a lot of stuff commercially, which I'm guessing is more useful. One of the things we have done is started up this thing called the Embedded Entrepreneurship Initiative. And what we have got are a whole stable of very successful kind of startup company founders, CEOs, that can either be advisors or even can be brought on as more intimate team members with DARPA-funded companies. These can be startups or existing companies to help them figure out what the trajectory for their technology is, whether that is starting a new company and building a business plan so you can get commercial investment, or whether that is finding the best and most useful way to license it. We have had a lot of success on that. I will be frank, a big part of this is the fact that we want, from a DoD perspective, we have to work a lot with US companies, and that means we need all of our technologies to get lots of good US investor money. And US investors are picky. They want like a guaranteed return on investment practically. So what we do is we're working very hard on figuring out what those commercial business models are to help make sure that the companies can go forward. Does that help a little bit? Or was that not what you're asking?
We're on the other side.
Okay.
So we're trying to figure out how to get some of your PM's work inserted into actual units. And we're trying to close that gap. I'm trying to describe, there's this, Crystal City problem where if it's not a program of record, it doesn't exist. How do we solve that half of the equation?
Okay. So multiple paths. And a lot of the things that we are doing, in fact, in some of our communications programs, we have decided to sort of bypass trying to become officially going into a program of record, and we've instead kind of adopted the subversive model where we get whatever relevant pieces of the software that we need into every program of record out there so that they wake up one day and suddenly realize they're addicted. Another thing that we have tried is actually taking our DARPA program managers, and when they leave, if they aren't already committed to a specific job, we're looking at ways where we can actually place them in the gaining organization so that they can then become the champion in the kind of the pull. We have done that, I think, quite successfully with the Air Force, and I'm having conversations with, kind of at the chief of staff level with each of the other services. I think that if DARPA is willing to pay those people salaries, which we are, and if we can get congressional permission, then we can start putting our own advocacy in is that kind of thing that would help if we could make that work for you?
Absolutely. Navy sooner, faster, please, if at all possible. Thank you so much.
Okay.
Hi, thanks for the great keynote. I was very happy to see like open source pop up on some of the programs, and I was like curious if you have like a consistent theme when that makes sense to call it out. Because I mean, you could say like for some, if you want to bootstrap industries, you would probably not want to go open source because you want companies to retain IP. In other cases, you might have like, I don't know, security concerns. I don't know. I was wondering if you had like a theme or like a common reason to say this is a program where open source makes sense and where it doesn't. So
the answer is no, we don't. Although I would think that most of our program managers, when they're designing this, they're going to go through, a pretty similar logic chain, and they're going to try to think about what is the best long-term chance of success for a certain technology to thrive. And the general assumption is the more closed it is, the more long-term resources have to be set aside to keep something updated, and and sort of healthy and relevant. So that's not a great model for the DoD. So as you can imagine, if we possibly can, leaning to an open source community, or even kind of maybe a closed open source community, but one where you have a lot of flexibility, is much, much better for not just terms of cost, but also for the chance that software will continue to update and maybe do things we had never imagined in the beginning. So, but the bottom line is each program manager, as they create their program, they are thinking through those kinds of questions. They're being quizzed and helped by a lot of DARPA experts that will help them get there, but that is something the PM has to care about and believe in and champion themselves.
And I have a question, if I may. At the beginning of your keynote, you mentioned how the launch of Sputnik was less a surprise to the scientists than it was to the politicians, and that was the impetus behind the foundation of ARPA. To what extent today is DARPA isolated from political concerns? Do you get to work? How independently do you get to work from, sort of the everyday congressional battles that we tend to hear about in the news?
So, as you can imagine, Congress has oversight of our budget, and we work very closely with both the House and the Senate, and with the sort of the armed services relevant committees all the time. We keep them up to date. They are extremely smart people, but primarily the staffers that we work with, but all of the members. Whenever we are in sessions with them, we find that they're asking great questions, and they really are kind of. We're lucky in this particular committee. They do a lot of homework. They think a lot about it, and they're very passionate. I did mention that, because we started 60 years ago, we have this great track record of success. That has allowed us basically bipartisan support, and they have worked, I think, tirelessly to make sure that we maintain the freedom and flexibility that allows DARPA to be DARPA. So, for example, if I really wanted to, I could hire a new program manager in about 48 hours. I probably don't want to. I mean, if nothing else, that person might need a chance to catch their breath. But we have that flexibility. Whereas in classic parts of the government, and I think Tom has experienced in this, it can take 9 months. There we go. Yeah, and nobody blinks. They just think, oh yes, that's the normal way of things. Of course, you're going to sit and wait for 9 months while you wait for your job offer, right? So. Same thing with the fact that we can start our programs without having to ask anyone for permission. We have a lot of these flexibilities built in. So we report to Congress, we're talking with them regularly, but we don't see them trying to interfere, and we have never really seen a political, sort of what you're thinking in terms of political influence pushing us to do our job.
Hi, good morning. My question is, how is the war in Ukraine affecting the investments that you've already made, or making you change investment, or where you place, energy and time and resources?
Sure. No, that's a great question. There are a couple of things that are happening. So one, I won't be able to talk about much, but as you can imagine, we went through our entire array of ongoing programs. At any moment in time, we have about 250 of them, by the way. We start like 50 new ones a year. So we looked at everything we had to see if there was anything that was either close to ready or could be accelerated where it could be useful. In any case where the answer is yes, as you can imagine, I'm not going to talk about it. But what we're doing that's a lot more interesting is we can look at the things that we're developing, particularly the really hardcore kind of military capabilities, and say, if the thing that we're doing had been available in February, what kind of a difference would it have made? And it allows us to really kind of test and challenge our own assumptions as to whether we still think the idea is actually relevant and game-changing or not, right? So, I mean, I'm really sad that this is being done at the expense of the Ukrainian people, but it's an incredible sort of way for us to learn lessons and kind of come back and rethink our assumptions. And I will say, in case you didn't know this, it was DARPA that created the Javelin missile. So we have had relevance in the past to which we can actually see the use today. So, yeah.
Any other questions from the audience? Oh, I see one over here.
Hello, I was wondering, is there any particularly interesting programs at DARPA that you could tell us about that you particularly enjoyed working with?
Well, so I have 250 children, and I love them all equally, of course. But you want me to talk about something kind of completely different? We have a lot of really cool things going on in the world of supply chains, not just semiconductor supply chains.
Is there any that you found like that was your favorite that captivated you, that you found interesting and might want to share?
Well, I think we're creating food out of we have two programs. One creating food out of thin air, using water and bacteria, and the other one creating food out of garbage, mostly plastic. So the plastic one is a little ahead. They've actually created nutritious food bars, but they won't let me taste them yet because they said that is not what they were optimized for. So they're still working on that. But as you can imagine, I find that particularly interesting for a whole variety of reasons. And then we have another program that is actually trying to extract water from air. Because there's a lot of new advances in chemistry, in sorbent materials. So the idea is that you could extract water even from really arid desert air that could sort of keep military units functioning, or we could use that water to create the food, right? So so that whole combination of things is particularly fascinating to me. My own technical background in DARPA is in positioning, navigation, and timing. So, one thing I find fascinating, not in the results of my program, but at the intersection of communities. So when you think of the communications world and you think of the navigation world, so much of what they're dealing with is exactly the same physics, and yet they're fundamentally different assumptions get them at loggerheads, right? So when you think about all of the concerns right now, I've already forgotten the name of the company because it keeps changing its name. But in terms of giving access to spectrum right next to the GPS bands and the fact that we can overwhelm those, there's I think both sides are making totally legitimate assumptions, but they're making them from their perspective. So a thing that I found perfectly fascinating as a concrete example of where we can go wrong has to do with when we were working on a program to try to navigate in deep multipath situations. And so we were using modeling and simulation software from the communications world and could not figure out why none of it matched reality. It took us weeks to realize that the developers were rounding off the speed of light to what was perfectly reasonable in a communications world, but we needed about 9 more decimal places for us to function. And that simple error, which nobody thought to ask about because both sides simply assumed that was the only way it could ever be done, caused us, in the end, almost like months of time wasted. So I throw that one out as particularly fascinating because I often come back to that when I'm looking at communities that are trying to cross over each other and they can't seem to get past these barriers. Sometimes there's these really interesting, very obvious in retrospect, but totally non-obvious problems that exist. So, for fun.
Hi, I'm very interested in DARPA's radio frequency machine learning systems program.
Yeah.
And I've reached out and tried to get the data set that backs up a lot of that research with the program manager, John Davies. And even though I work for a defense contractor, I'm unable to get that data set unless I have a government sponsor. So I would ask, is there any way that DARPA can maybe create data sets for RF that could be released to, if not the general public, at least the defense industry in general?
The answer is probably. Let me just make sure I write this down coherently. Do you have active government work of any sort right now? Yeah.
I needed a specific government sponsor to get an MOU to get this kind of data. And I know it requires a non-disclosure agreement. And I understand, all of that, but it would be really great if there were something like, and this sort of goes back to what Luke Bogner was talking about the other day, we need a little bit more data to help machine learning systems in something like ImageNet, but for RF would be a great way to start that process off.
Yeah, like the large language model data sets and things like that. Sure. Okay. No, it's a great point. I've noted it down and I'll try to figure it out. Who would I come back to if we have an answer? We just advertise it publicly?
I know that there is a lot of public research that's been out. Northeastern has used those data sets and published their research, as has Expedition Technology. If it gets published on Archive or IEEE, we'll see that research and pick up on it and follow those links.
If you can't, give me your name at the end too. My guess is that the earlier solution is probably not going to be something we would make totally public, but we could. I can't imagine why we couldn't make it available to folks who are working on existing government contracts. It seems like that.
It should be a low bar.
Yeah. Yeah.
Thank you.
Okay. Getting a workout this morning.
Hello again. So I'm from Germany, and we don't have like a exact equivalent of DARPA in Germany. But not only that, but just as a foreigner, it seems that DARPA is incredibly successful and popular. Like the DOJ is in the news all the time, and it's not always good news. But it seems like DARPA is always something interesting, and I don't know, maybe that's a biased view from outside. But what's your secret? Can you give advice to other people running organizations like that? To what do you have to do to run an inspirational quote to what do you have to do to run an organization like DARPA successfully?
Well, I will say that the UK is in the middle of creating their own. The Australians are trying to figure out how to find budget to create one of their own. Japan actually kind of has. A couple of other countries have been very interested. So it is fascinating to everybody. I think the secret sauce, the most important part, is that all of the technical people have to leave, right? So there are a lot of things. The fact that we have a lot of this freedom, we have congressional support, all of those things matter. But if you really want to be high risk focused, then right at the point that you get comfortable in an organization is when you should leave, because comfort tends to counteract your risk tolerance, right? So, one of the jokes is that the two things that stop you from wanting to take risks are failure and success, right? So failure is obvious. People tend to get real timid, but success is just as insidious, because the idea is that the next big idea might obviate what you did before. And so people have a really hard time with the fact that they might have to give up something that is stable and successful and that they made their name on and they're really proud of with the next big thing. So there are a few human beings, I think Steve Jobs comes to mind, who are sort of intrinsically able to kind of trash their past in order to create the next thing, but most of us aren't wired that way. So the organization has to be. So this fact that, right around the 4 or 5 year mark, we leave, and that includes me and it includes all of the technical people, I think is one of the really important secrets. So, but it helps to have a generous budget and the flexibility to make decisions quickly, of course.
All right, I think we've got time for one more question, and then we'll move into the break.
So I had a question with how quickly some technologies advance. So a lot of people are looking at quantum for encryption. If something like that becomes an alternative to kind of past methods, does DARPA kind of get rid of all of their older encryption projects, or do they kind of see them to fruition to see if there's maybe a change?
So if that were to happen, and I'm not actually planning on it in the next coming months, it would be a case-by-case basis, right? You'd have to look at what an encryption program was created for and whether or not it was relevant for the class of problems that one had. But we have actually two programs right now really trying to look at this question of quantum computing and whether or not there's a there. And, and the jury is out. But when we talk to physicists, it's really almost like 50-50. Those that are absolutely convinced that quantum computing is going to change everything, and those that think that it will result in basically nothing. And even with Shor's algorithm, kind of the one algorithm for which we have at least theoretical proof that it will be useful, we have not yet been able to demonstrate it at kind of utility scale, where you sort of, effectively you get more out of it than you put in. And so we have a program called quantum benchmarking, which is trying to help us understand like what we would really be testing for and looking for in the quantum computing domain, and how we would then understand whether or not we were moving forward. And then we have one focused on utility scale quantum computing, which is really trying to tap into all the commercial investments that are out there to figure out if there is a vector of strategic surprise that we just don't know about. But to everything that is public and everything that we have knowledge of, it hasn't been demonstrated yet. So.
All right, and with that, thank you very much, Dr. Tompkins. It was incredible, very interesting.